Okay, let's get started. So welcome to this session about quantum-safe cryptography or post-quantum cryptography. This is quite new, I guess, to many. It's kind of an effort that had been ongoing for roughly 10 years and kind of converged against some new schemes that will now be standardized in different countries and be used in different protocols. And in this talk, I'll go a bit into what this new post-quantum cryptography is and some of the upcoming challenges and also some opportunities coming from this field. So just 2 words about myself at first. So I'm a security and cryptography expert at Pwn Biometrics, a startup here in Oslo, working on secure authentication and have an off-pad card for passkeys, so you can log into digital services. And we're working with how to implement cryptography on embedded devices and how to use biometrics to authenticate yourself. And recently looked into how to embed quantum-safe cryptography into this framework. But most of my time, I'm a associate professor in cryptology at NTNU in Trondheim, and I'm working on quantum-safe crypto. So kind of what I'm going to talk about today is what I spent my last, I guess, 7 years of my life working on and try to convey to you in an accessible manner. And I'm also teaching there, so I'm teaching secure cryptographic implementations, and it's really fun to see kind of how to use these algorithms in practice, what kind of challenges you face, how to solve them, and so forth. And I'm currently supervising several master's and PhD students in this topic, and this is kind of knowledge gathered through different projects over the years. So my high-level overview for this talk is I'll talk a bit about cryptography today to start with, because quantum computing, that will be the next topic, kind of affects the schemes that we use today in different ways, based on kind of the underlying primitives and how we use them. So it's not equal for all of them. Then I'll talk slightly about quantum computing, just what is this, why does this help us, or why is this scary for cryptography? Look into quantum-safe cryptography, and this is the only section I would say that is also slightly technical. So I have a few slides on what kind of cryptography we will actually start using, but otherwise it will be somewhat high level. We'll look at the store now, decrypt later attack and kind of how to mitigate that. And end with some conclusions, both on the challenges that we face and what you kind of will face in the coming years if you are on the side where you need to implement or use post-quantum crypto in some way. And also some of the opportunities here, maybe mostly as a community, but also like for individual companies and people. So that's kind of what I'll go through. So just to recap slightly, and for some of you, maybe you attended a talk on crypto yesterday, so this will be similar, but just so that we're all on the same page. Like we have different ways of using cryptography, different kind of primitives, different kind of properties of cryptography. But in general, we divide them into public key and symmetric key crypto. And for public key crypto, we have public key encryption, right? So you have some message. You want to encrypt it. Anyone can do that with a public key of the recipient. You get a ciphertext, so both the public key and the ciphertext might be public and anyone can see it, but only the party with the secret key is able to decrypt and read the text. Okay. Furthermore, we have digital signatures. Again, you have a public key, but it's kind of, what you do is kind of the opposite. So you have some kind of message. This can be arbitrarily large, so like files of megabytes or gigabytes, doesn't matter. What you do, you hash it so that you get a fixed size message that is kind of the fingerprint of the file. And you can sign it with a private key so that anyone holding the public key can verify that you signed it. Okay, so these are kind of well-known primitives used basically everywhere today. And furthermore, we have symmetric key crypto. So in this setting, the two parties then have a shared key already. So in the other setting, in public key crypto, you only know the public key of other people. But here you have a shared key already set up with the party you want to communicate with. And then you can encrypt using that key, and you can decrypt using that key. And there's no like public information, except for the ciphertext, might be sent between the two parties. So one example, and which is kind of what happens whenever you connect to a website and you want to communicate securely, you do a key exchange. Nowadays, mostly with the Diffie-Hellman protocol. And this is based on the discrete logarithm problem. So this is kind of the mathematical foundation that ensures security of this protocol. So if you look at it briefly, the green values here are public. So you have some kind of what we call a generator, but it's like a public element, say a number, and you take it to a secret exponent. And then you do a modular reduction from a big prime, which means whatever number you did to get when you took this public element to your secret exponent, you reduce it so that you only keep the part that was smaller than the prime. Okay, it's like when we do calculate the time of the day, right? If it goes over to the next day, you only care about the time of the day. Okay, it's the same concept. So you do that, and then you send this result to the other party. They do the same thing, and whatever you receive, you take to your secret exponent again. And then by combining them, you then end up with the same value in the end. And you can use this to as a secret key in AES, for example, to encrypt messages back and forth. So this is one way to do a key exchange and then encrypt information. And the security of this protocol is that given the common element that everyone knows, and the prime, and the result, it's hard to find the secret exponent that you chose. So this is what we call the discrete logarithm problem to break this scheme. So if that problem is hard to compute, then this protocol gives you security. Okay, and you have a similar setup with RSA, which is quite commonly used as well, where prime factorization is the hard underlying problem that as long as no one can factorize large biprimes, so a product of two primes, then the protocol itself is secure and you can communicate securely. Okay, so this is kind of the underlying problems that need to be hard for this to give us security. So if we look a bit at the problems or the algorithms we have today, we use RSA, which is based on factoring, both for encryption and for signatures. We have two versions of the other protocols. We have this kind of exponent modular prime that I showed you, and we have an elliptic curve version of that, where instead of computing on numbers, you're computing on points on a curve. And they have like both of them reduced to this discrete logarithm problem that I mentioned. So here you have Diffie-Hellman, you have digital signature algorithm, and you have El-Gamal encryption, both based on elliptic curves, and modular arithmetic, modular prime. You also have pairings, which is also based on the same problems. This doesn't come up so often, but maybe you've seen zero-knowledge proofs in different blockchain applications and so forth, based on the same underlying hardness problem. Okay, so again, we need these mathematical problems to be hard, otherwise we have no security at all. And as far as we know, if we look at the best ways to compute these things or to break these problems, these are exponential in the size of the prime numbers that are used. Okay, so if we want, we often talk about bit security in a protocol, so if we want 128 bit of security, that means that an attacker should not be able to break your protocol doing less than 2 to the 128 operations. Okay, so we need to make sure that when we choose parameters for these schemes, the best algorithms runs in more than 2 to the 128 operations to find a solution to the problem. Okay, so this is kind of how we estimate security. Like we cannot prove that something is secure, we can prove that something is as hard as another problem. And if we don't know how to break that, well, that then indicates that the scheme is secure. So it's like a reduction that you might have seen in an algorithm course or something. And what's interesting about public key encryption is that all of these schemes rely on a specific underlying, say, number theory or algebra problem like factoring and discrete log. But symmetric schemes, where you already have a shared key or something. These are more like scrambling algorithms that just mess things up. There is no reduction to number theory or algebra below. And they kind of behave differently. So it's a bit more like we designed the AES symmetric encryption scheme so that the best known attack is brute force. We don't know how to do better. But with factoring, it's like we do know how to find primes easier than it is to try all numbers. So like this makes a difference that you can potentially speed up the attacks and you need different kind of parameters. So this is why we use, for example, RSA 3072 in TLS and other applications, because the attacks are much faster than brute force, because otherwise it would have been a 128-bit prime number instead. Okay, and the similar things with the hash functions and MAC schemes. So these are kind of two different families, and they have underlying, like the public key ones have underlying problems that we want to prove security based on some number theory or algebra, but the other ones are kind of scrabbling things up. Okay, and we use these like everywhere. So this is just some examples, not an exhaustive list. But like whenever you want to communicate with friends, family, whoever, you might use Signal or WhatsApp or iMessage to send messages that you want to keep private, and those are encrypted. You use TLS, for example, to connect to websites. You have some kind of digital authentication scheme based on where you live to connect to government services and so forth. And we all have, several payment applications on our phones that we use every day to pay for whatever we're buying. And all of these are based on these cryptographic algorithms, and usually a combination of the categories. You often use public key crypto to establish a connection, or maybe to ensure that someone are who they claim to be. But you use symmetric key schemes when that connection is established for the communication going forward. And I think there's a question.
So my question is, so I see that on secure messaging you have Signal, WhatsApp, and iMessage, but is Telegram here? Because I see a lot of people like tap forward using that, but I don't think it has like end-to-end encryption, right? So I would say it's like less secure, but everyone says it's very secure. So like, is it really secure?
So that's a good question. So it's about why it's not Telegram listed as a secure messaging app here. So again, I just want to emphasize this is not exhaustive list. So like there are many applications not listed here that are still secure. For your specific example, as far as I know, Telegram is very similar to Signal and WhatsApp, but it's not end-to-end encrypted by default. You need to turn on secret chat.
So it's less secure actually, right? Like
Potentially less secure, yes. And also you can not have end-to-end encryption for group chats, which is possible in the other applications. And they also using their own cryptographic schemes. So this is maybe the biggest one, like biggest red flag for Telegram. But if you care about it as a social media, it's great as a broadcast channel, but I wouldn't maybe use it for private communication. Yeah, good question, thanks. Maybe I should have said that up front, like the other talks at the conference usually have questions at the end, but feel free to ask questions during the talk. I'm probably going to switch between a few topics, and it's good to just take it when we have the slides up front. Yeah. Okay, so then the question is, like, we have these amazing applications today, problem solved. We can communicate securely. And then the question is, will these protocols and schemes that we discussed, will they be secure in the future? And then the problem is, or potential challenge that we will face in the coming years, is the development of quantum computers. So it's been invested, I would say, billions of dollars. A lot of talent been working on this for many, many years. We have seen some recent results indicating that quantum computers are becoming feasible. Like in theory, it works. Okay, so we already, and we'll see that we have some results that in theory breaks all or most of the cryptography that we use today. Okay, but then the question is like, are we getting there ever, right? And this is kind of hard to say. These machines are like very special in that they need to be kind of isolating atoms for computing on atoms. And it's a kind of engineering problem, so to speak, that can you even build these machines? And they get really like impacted from the environment around them. So even temperature change in the room would kind of affect computation. So it's really sensitive in that sense, and it's kind of something that people are working on to solve. Can we do this? So just let's look 2 seconds for what quantum computing does, but question first.
Just interested, why are they quantum computers always upside down?
I have no idea. Okay. Yeah. So this is a common one, like in my drawing as well. I think it's just the way people found out how to really like make these isolated atoms, but don't ask me about the machine itself. But yeah, it's funny, right? It looks like I don't know, something from the future. Anyway, so like we all kind of used to classical computing, so that's the word I'm going to use. Classical computing is how you work on bits, right? And they can have 1 out of 2 value, power on, power off, and you can manipulate them, and you can have many of them, and they can depend on each other, and you do computation that kind of we learn about Turing machines and like what's possible to compute and not, and how do you manipulate these, and we have formalized this in programming languages, and we know kind of how to compute functions using bits and higher level abstractions. So qubits are a bit different. So here you don't really have a certain value of the bit. Like think of it as a bit in memory. It's not 0 or 1. It's you don't know. It could be one of them, but you don't know before you look. Okay? And if you want to do computation on it, you need to do the computation on it before you look, because otherwise this quantum state collapses and the value is kind of fixed. So this is not like a super accurate description of the physics, but it's kind of how I like to think about it from a computational perspective. Okay, so again, you can have 1 bit, you can have many bits. You can have like a vector of this, and you want to compute some function on this vector. And you cannot, before the end of the computation, actually have a look at the result. And one kind of misconception here is that people think quantum computers can compute anything at once in parallel universe. Okay, so this is quite inaccurate. What is true is that you have a probability distribution of what kind of value the bit has. Okay, so you can compute on it by manipulating this probability to give you with some probability the result that you want in the end. Okay, so you want to kind of impact and do computation on these bits so that it gives you something useful in the end, but it only gives you one answer, and it gives you the answer according to this probability distribution. So you don't get, all possible answers. You don't get, all prime factors. You might get, when you're trying to break RSA, you might get some information that is useful and related to factoring, but you don't get like one solution guaranteed. So we need to kind of be a bit careful when computing and when designing algorithms for qubits, is that you don't really you can't really enforce the answer you like. You can just kind of impact the computation so that it's likely to give you what you want. Okay? And what you also have with qubits that is not something you can do with normal bits is what's called entanglement. So usually with bits, you want to compute them, and they're kind of behaving. You can do something here and something there, and this kind of doesn't impact each other. But with qubits, you can kind of link them together so that if you do some computation on one bit, this might impact the other bit as well, even though you didn't do computation on the other one explicitly yourself. And this allows to do something else. So this is kind of my main point here. It's a different way of computing. It's not necessarily a better way of computing. Actually, I would say in 99% of the settings, it's not better. It's worse, much more worse, because it's so difficult, it's so expensive. We don't know how to do it with more than just a handful of bits or qubits. So this is like really like in most cases, this is not useful at all. And recently, I think it was Google actually announced a $5 million competition to come up with useful applications of quantum computing. Right, so we have invested like billions into this, and now we're trying to think what we can actually do with this. Is it useful in any way? But one use case that we know of is actually like breaking cryptography. Okay, but can we do something more proactive, right? That's kind of the question. And so I want to emphasize this point. It's just a different way of computation. In very specific settings, we might be able to compute something in a faster and better way than we can with classical computing, but in general, we cannot. So let's move on. So there's basically two algorithms in quantum computing that kind of impacts cryptography. One of them is Shor's algorithm from Peter Shor, published in the 90s. And this algorithm is very efficient. It's a quantum algorithm, and you can find the periodicity of a function. So like when a function repeats itself. And this can be applied by thinking of the RSA encryption algorithm as a function, or the Diffie-Hellman key exchange algorithm as a function. And this can be used to factor or to compute discrete log. So it's kind of by coincidence, like the one really efficient quantum algorithm we know of, by accident, is very efficient to break the cryptography that we use. And we haven't really found many other interesting applications of it. So like, what's the chance, right? So this is really efficient, in theory, to implement on a quantum computer to break public key encryption schemes. We also have another algorithm that is interesting, and that's Grover's algorithm. And it doesn't give us the same efficiency that Shor's algorithm, but it does help us to speed up computation, and in general to do search or solve just brute force search problems. Basically, we can speed up this kind of computation. So for example, if we want to break AES, I mentioned that AES is designed so that the best attack that exists, or at least as we know of, is brute force search of the key. Okay, and this algorithm will then help us making this brute force more efficient. In practice, as I didn't put it in the slide, but it does give us a square root speedup, which means that if we have a 128-bit key, we can brute force it in 2 to the 64 operations, so half the bits. And similar speedups apply to finding collisions for hash functions. This is also some kind of brute force problem. So if we then summarize, based on the cryptography that we use today, then we see that all the public key schemes that I mentioned are just dead. If such a quantum computer of large enough size is built. Then we have algorithms that we could implement on these computers, and they would break them. And in theory, breaking them is as efficient as using them. Right? It doesn't give us anything. But for AES and hash functions like SHA-2 and 3 and HMAC and so forth, we potentially can brute force faster. There's still some discussion ongoing on this because it requires so much effort and memory and so forth that it might actually not in practice give us any speed up. But at least in theory, we would have to double the bit size to preserve the security that we have today. But this is actually not really a problem. So for AES, we often use 128-bit keys. We already have AES 256 standardized. This is available today. For SHA-2 and SHA-3, the hash functions, those usually give outputs of 256 bits. Collisions takes 2 to the 128 to compute. But we already have hash functions today with outputs that are either 384 bits or 512 bits, already standardized. You can use it today. Problem kind of solved. You might need to do some changes, right? But it's already here. It's already standardized. There's really still a big gap between using and breaking, like an exponential gap. Not as big as today, but still something that gives us security. Okay, this is just gone for public key encryption and signatures. So then we need to replace this with something, and that's quantum safe cryptography or post-quantum cryptography, PQC. This is cryptography that we still run on our computers that we use today. Okay, and this does not mean that everyone needs a quantum computer in their pocket to send private messages. This means that we replace the cryptography we have today on our classical laptops and phones, and we use this instead. But we build these schemes on other mathematical problems than factoring in discrete log, which we know how to break in theory with a quantum computer, with other problems that we believe are hard, even against quantum computers. Of course, as I mentioned earlier, we cannot really prove something is hard. Like for everyone in computer science, we know that we don't have a solution to P versus NP. We cannot prove that something is like always going to be hard to break. So how we ensure security of cryptography is that we build a protocol for, say, public key encryption based on a mathematical problem, saying that if you can break the protocol, you can break the underlying problem. So then we need to analyze how hard is it to break this problem. And then we look at the best possible attacks with classical or quantum computers. Okay, and what is the running time of the best attacks that we know of? And then we ensure that the parameters we set makes these algorithms infeasible to run in practice. So doing 2 to the 128 operations, relative to the computing power we have in the world today, this would take every computer in the world running to break one key until the end of the universe. So that's kind of how we set security. Like, it should be infeasible for all future, except if this quantum computer comes up. So then we study quantum algorithms, like how do they potentially speed up the attacks on these new problems, if at all. And then we try to understand them well enough so that we can set parameters for these new mathematical assumptions. And there's a few families of problems that are kind of people have been looking at and that we're about to, or is about to standardize. These are lattices, codes, isogenies, and also symmetric schemes. So I mentioned like AES, potentially you need to double the key size, but otherwise we're fine. And we can actually design signature schemes only based on AES, like symmetric key schemes and hash functions. So like we know how to at least design a new scheme there for signatures that would be secure. For public key encryption, we don't know how to do it from symmetric primitives, so we need something else, some kind of mathematical number theory algebra problem. And these are the lattices, codes, and isogenies. And we're going to look a bit on lattices, so this will be my 3 technical slides. And we have an underlying problem here called learning with errors. This problem is actually coming from machine learning. Like, you have a lot of noisy data, and you want to kind of design an algorithm to kind of, give you some output so that you can represent all of this noisy data in an accurate way. And then there is a lot of noise that you want to get rid of. And this is how people came up with this problem, actually. They wanted to show that this was possible to compute. They couldn't. And then they said, well, what if it's so hard that we can build cryptography on top of it instead? And then we did that. So now we need to recall what we learned in the linear algebra class in undergrad. So learning with errors and lattice-based cryptography is based on matrices and vectors. Okay, so this blue big box, this is a matrix with elements. And this is going to be public. And what we know from undergrad is that, well, if we compute a matrix, which is public, times the secret vector, and then we get a new vector. And if this one is public, then we can use Gaussian elimination to find a solution to this linear system. Okay, so if we, for a second, we just ignore the yellow vector, and we say that we know the blue, we know the brown, and we want to try to find the orange one, we have algorithms to do this. Like you could hire any 20-year-old from a technical university, and he will be able to solve this problem for you. And then what we do is we add some noise to it, a tiny bit of noise, just change the equation slightly. And these orange and the yellow vectors, they had to have short values. So think of RSA, for example. Okay, the moduli there we're working over is the product of two primes of the size 3072 bits. These values here are also working in this kind of modular arithmetic. So whenever you get a number that is too big, you kind of chop it off and only keep the part that is smaller than your moduli. But for these numbers, the moduli is more like 20 bits, so like 2 to the 20, roughly. But all of these numbers are of that size. Uniform elements in the blue matrix modulo this 2 to the 20 moduli. But the orange and the yellow one, those are binary or ternary, so only like 1, 0, -1 values, very small changes. So given the blue one and given the brown one, the problem is to find the orange and yellow one, and they had to be short. So you're given some bound, you need to find the vector that satisfies this equation, but all of the coefficients need to be binary, for example. And this is a hard problem, even for quantum computers. Essentially, it's exponentially hard in the dimension of the blue matrix. So the larger matrix you have, the more security you get. And if this, again, if it wasn't for these noisy equations, we know how to compute or break this or solve this system for even millions of equations. But for cryptography, because of this smallness requirement and that everything is modulo some prime of 20 bits, if this blue matrix is of size 500 or 1,000, this gives you 128-bit security against a quantum computer, roughly speaking. So here we have this underlying problem. You're probably going to face this a lot in the coming years, learning with errors, and it's based on finding these secret vectors of short coefficients. So this is the second technical slide. So how can we use this problem to build cryptography? Well, so the public key in your system is going to be this public matrix, the blue one, and the purple one on this slide. So the blue one is kind of public parameters, and the purple one is the public key of you specifically, while the orange and the yellow ones are your short secret key. Okay, so if this problem is hard, then no one can find your secret key. And then we use the same thing to encrypt the message. So what you do is you have this red message, and you use your public key, and again you multiply it with a short vector, and you add another short vector to it. Okay, so then you have another of these learning with error samples. You create a fresh one based on your public key, and you add a message to it. So if it was hard to break in the first place, if this result of the learning with errors problem was uniform, you can't tell the difference if it's uniform or if it's uniform plus a specific message. They have the same distribution. So this is how we then encrypt the message. And if we have the secret key, then we can multiply the ciphertext with the secret key, take the difference, and the message pops out. And one thing to notice here is that you have an approximate sign there. It's not equal because of these noisy equations. Okay, so the more noise, the harder to break, but you might mess up the message. So when we set parameters for these schemes, we need to make sure that it's enough noise to give you security, but not too much to break correctness of your scheme. So you kind of need to balance this out. So you need some kind of decoding mechanism, but because you get roughly the message back, we do know how to kind of error correct and get the actual message back. This is kind of built into these schemes. But essentially, your public key is a learning with error sample, and your ciphertext is a learning with error sample, and then you can do some combination to reconstruct the message using the secret key. So this is what's happening, and this is what is now being implemented and standardized as the Kyber scheme. So for signatures, it's a bit similar, but also a bit different. So the public key, again, is a learning with error sample. Okay, so if this problem is hard, then the public key is secure. And what we're going to do next is a bit similar to what we do for the elliptic curve signatures. Okay, so the high-level structure is a bit similar, but the concrete details are, of course, very different. But in Schnorr signatures or ECDSA signatures, what you do first is you sample a random element. You take, multiply this with an elliptic curve point that is public to get some kind of fresh nonce value. And then you hash that together with a message, and then you give a solution to a specific equation based on the secret key. So that's what we're going to do here as well. We have the public key is the blue one and the purple one. And the secret key, in practice, that's the orange one and the yellow. So what we're going to do, we sample some fresh short randomness. This is the red and the green one. And we again produce a learning with error sample, just like we did for encryption and for the public key. So we do another sample. Then we take our message, in this case mu, together with this sample and hash it. And then we compute the solution in the end, which is the orange one, that's the secret key, times the challenge, plus a mask, which was the fresh randomness used for the signature once. So the red one is hiding the orange one to not leak your secret key. And similar for the second part of the signature, you take the yellow one, which is a part of your secret key, times the challenge, and mask it with a green value, again from your learning with error sample to begin with. And that's going to be your signature, these two masked values and the challenge. Okay, so this is similar to elliptic curve signatures. You get some random mask, you hash something based on this and public information, and then you use your secret key to answer some equation. And then a verifier can then check this later. So here, the verifier, I didn't include this in the slide, but you take these two values, you check some linear combination with the public key, and that the hash was correct, and then you accept. But again, you see that it's many of these learning with error samples happening. And this is the security of both of the schemes. Yeah. Okay, so let's move on. So if we look at the timeline here, we knew about quantum computers since a long time, and we knew about quantum algorithms for breaking cryptography since the 90s. And we also have lattice-based cryptography. So what we're standardizing today was like the starting point of this field actually were also in the 90s. So we have results from the 90s, both from 96 and also from early 2000, from 2005, saying that this learning with errors problem is secure. Like you have kind of reductions based on hardness that these problems kind of gives us a strong indication that this is secure. So we have, in practice, we have a reduction for these problems to something that is NP complete. If, NP is not equal to P, then this gives us some kind of confidence that this is a secure problem to build cryptography on top of. And then there's been a lot of research on lattice-based cryptography. And in 2016, the National Institute of Standards and Technology in the US, NIST, decided to have an open competition to standardize post-quantum crypto. So this is a bit similar to AES, 20 years earlier, when we wanted to have a symmetric key scheme that everyone could use. And we had an open competition where two researchers from Belgium won, and that's what we call AES today. And they wanted to have the same thing. So anyone from the world could submit their own quantum secure key exchange or signature scheme for evaluation. And there was 69 schemes in 2017 that was published that we will standardize some of these. And everyone in the world could then look at it and study and try to break it, and broke many of them, and see kind of what is the security of these schemes, so that we get international consensus that we trust some of the schemes, and then we standardize those for usage in the future. And last year, or 2 years ago, they were defining 4 schemes that they wanted to standardize, and the standardization documents were published last fall. So I'm going to mention 2 of these 4, because there's 2 of them that is kind of general purpose schemes that they want people to use for key exchange and signatures. And then they additionally standardized 2 signature schemes, and there are ongoing processes of standardizing more key exchange schemes and signature schemes. But these are kind of the 2 that they expect people to use in general for most applications. So one of them is the candidate that was submitted was called Crystal Kyber, and the standard will be module lattice-based key encapsulation mechanism, or ML-CHEM. So this is going to be the acronym that you will see going forward, ML-CHEM. And this is essentially like this encryption scheme that I showed you on a previous slide. So this is coming. So how does performance look like? So I included only sizes here, but what we can see immediately, if we think of RSA, 3,000 bits, that's roughly, say, 400 bytes. And here we see that the smallest parameter set for Kyber, or for ML-CHEM, gives you a 800-byte key. That's for public key encryption, essentially. For decapsulation, it's twice the size. You have a ciphertext, which is also, roughly 800 bytes, to get the shared secret that is 32 bytes. So here we see that this is at least twice the size of RSA. And if you compare to elliptic curve schemes, which are all roughly 32 bytes for both public key encryption, like the public key, the secret key, the ciphertext, everything is just 32 bytes. It is, an order of magnitude larger, at least, like a factor 20, roughly, in size. And of course, this will impact a lot of use cases. For example, in TLS, where you have packet sizes that are not below this, but at least below, the larger parameter sets, and also for signatures, that's going to be a problem. We actually need to send several packets to include one key or one signature. So we have to pay something for this, like in size, to get quantum security. I didn't have benchmarks here, but in general, linear algebra on a computer is super fast. So these schemes are usually actually faster than the schemes that we use today. In particular, elliptic curve cryptography is quite complicated to compute, so it's often much, much faster using lattices than elliptic curves. So you kind of have this trade-off between something that is faster but larger. The second one is dilithium, crystals dilithium, or MLDSA, which will be the new acronym there. Again, this is essentially the signature scheme that I showed you on the slide. Looking at sizes again, this situation is actually worse. So here, the private key and the public keys are even larger than for ML-CHEM. In this scheme, you actually do have some flexibility when they designed it. So not in the standard, but when they designed it, this masking process that I mentioned, what you have is something called rejection sampling. because if you output the signature, it might leak information about the secret key sometimes. And you want to avoid that. So sometimes you need to just throw away the result and restart your computation until you get something that doesn't leak information and you can output it. So there you can do this trade-off. You can set parameters so that you often reject, but when you don't, you get a small signature. Or you can enlarge the parameters so that you more rarely reject, so then you do less computation, but you get a larger signature. And for dilithium, I think what they chose was that you expect roughly 10 trials before you succeed to produce a signature and output it, because it's so fast but bigger. So you want to kind of compress the signature as much as you can while still having a performance scheme. So these are the sizes for dilithium, and again, there's a lot of challenges that are coming to integrate this. So how do we integrate it? Well, let's see. NIST have a report giving recommendations for how to do it, but this is very fresh. Like, I think people are just started looking at how do we do this, because as I mentioned, the standard was published in the fall. But I think one of the key points here is crypto agility, which is one of the main points of the Think library talk yesterday, that you need to have a library where you can replace algorithms easily, so that you can kind of continue working with it and use it, and that you have some kind of flexibility when you swap in and swap out algorithms that are either secure or should be post-quantum secure. So I think that's one of the key points, but this is just in the starting point, and a lot of companies are now looking into what to do. But this matters actually today. Like I mentioned, quantum computers, they're like really difficult to make, and we just have a few qubits now possible like for computation. So it's not really a threat today, but we still need to care about it today. And the reason why is we encrypt a lot of information today that has value in the future. So we're sending ciphertexts over the internet, and we know for a fact that nation states across the world does store information being sent on the internet today. So if you have valuable information, then this might be available to an adversary in the future when a quantum computer is built. Of course, this depends a lot between people and companies and so forth, but like nations have a lot of secrets they want to keep, and often things are stamped, for 50 years this should be secret and so forth. What I'm sending on as a message today might not matter too much, but if it's health data, like I'm still me 50 years from now, right? So this might still be important to me and things I want to keep private and so forth. And I think everyone have, something that we send today that still is I want to keep it private in the future. Another example is electronic voting, right? So this is not something that we actively do in Norway, but if you go to Switzerland or Estonia and Australia and France and other countries, they do use electronic systems for voting based on cryptography that is not quantum secure. And in a modern democracy, we want to keep votes private, even in the future. So what we need to think about is kind of this inequality, how long time does it take to transition to quantum safe cryptography? And how long do you want the data that you encrypt today to be secure? And when do you think that classical cryptography will be broken? Right? And then you have this kind of equation is your data safe or not, based on your belief when this will be possible. And some experts says it's going to happen in 10 to 15 years. Some have said it's going to happen in 20 years, and they've said it for 20 years. And we don't know. I don't think anyone knows. I don't think we have it today. But it might be that we won't know the day it happens. Because a lot of these investments happens by nation states, and if they succeed to build one that can break cryptography, they might not want to tell us at first. All right, so we need to prepare already today because we have a lot of valuable information that we will send and store in the coming years that we want to be able to protect also in the future. And I found this lovely tweet, I think it's from 2018 or something, you know, when Twitter was still fun, that like who you talk to online, like you might have a private conversation, but if your signature scheme is broken, that only means that you have a private conversation with the adversary, right? So it really matters, like for both signature schemes, there's no like future in security, but we need to be ready the day of, or rather the day before, right? But for encryption, there's a lot of information flowing around today that we also need to protect for the future. So both of them matters, maybe encryption more than signatures right now, but it has to be in place before it's there. Think getting an update to your laptop, if the signature for that update is broken, then someone can put the backdoor into all laptops in the world. Right, so it really matters that this is ready before. So for the US, they do have a timeline. So this is essentially NSA saying that everyone who wants to work with the US government need to update certain aspects of their portfolio with quantum safe cryptography, either by 2030 or 2033. And that's not many years from now. Like, that's almost tomorrow. So this is like really happening right now. This is a mandate. This is like what they require from people. As soon as the standards are ready, you need to start working on it because you only have a handful of years before this must be in place. And they actually say you need to offer it earlier, and they only accept post-quantum crypto after this deadline. So in the US, they're really like, switch to post-quantum crypto. This is already approved. You can use it today. We approve you for only using this today and forward. European agencies are a bit more on defense. Like these lattice-based algorithms, yes, we've been working on it for a while, but like, are they really secure? Can we mess it up? And so forth. And they want to have hybrid so that you can combine the new ones with the old ones, and that as long as at least one of them is secure, you have security. Okay, so maybe the classical one can be broken, but the post-quantum one give you security. Or maybe there's a flaw in the post-quantum one that we didn't know of. At least you have not less security than you already had. So they want to kind of combine this, that when you do a key exchange, you do it with two algorithms, and then you combine them in some way to encrypt with AES afterwards. Or if you have a signature, you want to produce two signatures, and you check both of them for the same message to verify. And we have some examples in practice already. So Signal, that I mentioned earlier, actually have some post-quantum security today. So when you establish a connection the first time, then it's both classical and post-quantum using Kyber. But only when you establish the connection. And then you have a lot of underlying mechanisms to kind of evolve the key over time and so forth. But this at least gives you a security from day one, but with a long-term post-quantum key. So if that's broken at some point later because they hack your phone or something, and then they break the classical schemes, then they might break everything. But this is kind of, it does add on for the security. Apple took it a step further. So they also do continuous key agreement, both classically and post-quantum. But because the keys for post-quantum is bigger, they don't do it for every message like they do with the classical one, but they do it for every 30 minutes or every X number of messages, just so that they kind of spread out the information that they need to send on top of their messages. But so that's a step further. Like even there, you only if you break one post-quantum key, you only get messages for one small epoch, not for the whole conversation, like you would do for Signal if you can break everything. if you look at TLS, this is already, post-quantum crypto is already available if you run, I think, Chromium on and connect to Cloudflare servers, or servers hosted by Cloudflare. And this is a graph for how many percentage of the internet now is post-quantum secure. And if you see all the to the right in the graph, this is today, so roughly 30-something% of internet is already running post-quantum secure key exchange. It's kind of happening under the hood, right? You don't really notice. It's still fast enough so people don't care. And then it's more about all the servers out there to kind of upgrade so that they support it as well, because the browser already does. And that's the first choice if you pick algorithm suite when you connect to a server. Question?
Do you know in Norway, do you know what, for instance, law or skatteetaten or DB or
Okay, so the question is about Norway and public services and their setup. I don't know any particular things. If they host it, say at Cloudflare, then they might get it already. You can go into Cloudflare website and their overview where I found this screenshot and check for countries and so forth. But for specific companies, organizations, I don't know. But I think if they do, it's probably not because they intended to do it, but because they got it offered automatically. But this is my guess. Yeah. But it's very interesting, and I think we will see more of this in Norway coming forward, because NSM published cryptographic recommendations this fall saying that you should prepare for a post-quantum transition. I don't know specifics except for companies like Thales and Kongsberg and so forth. I know that they are working on it for their own services, but I don't know for any others, no. Yeah. Okay. A few more minutes. So you can do the same thing with FIDO. And this is kind of where our company worked on this for how to do signatures in a FIDO framework, giving you post-quantum security. And we saw that using passkeys like these, softpads, we can add post-quantum signatures to the FIDO protocol, and you can verify the signatures, like both of them on the message, and it kind of works into the framework as is. Of course, we needed our own kind of hand-picked codes to allow for this kind of what kind of algorithms you pick, but this is easy to set up, and it's kind of already there. So you can basically just add another signature scheme on your passkey. It goes through the protocol, you just encode it as you would normally, and you need the server that then checks both. So, of course, we tested it locally, but any company could set this up, have a server code that checks 2 signatures instead of 1, given a passkey that would offer that. So I think this is kind of somewhat easy, and I know that the FIDO Alliance is already working on adding quantum secure signatures to the framework. So there will probably happen something there. If it's going to be hybrid or if it's going to be only post-quantum, it's not decided yet. But at least we wanted to test, is this something we can do? Does it run? Does it fit in the already existing framework, or do we need to do a lot of adjustments? And essentially, we just needed to do small changes on the server side to verify too, and of course, add signature schemes on the device itself, but this is something that we controlled, so that was kind of easy. So this is already possible, and I know a lot of people are working on similar things. So let's conclude. So there's some challenges. One of the big ones is the size of ciphertext and public keys and signatures, and it's small amount of data. If you think of connecting to Netflix and you're watching a movie, this is only for the setup connection, right? It doesn't matter. But it does matter for the underlying protocols that might have restrictions for how much data you can send in certain protocols like TLS and SSH and so forth. So it's something that you often need to take care of on a protocol level, but doesn't really matter much for the application. Same problem with memory, that there's a lot of data you need to keep in memory and a lot of data that you need to compute on. And while it's mostly faster, so all the lattice-based ones are really fast, but there's other alternatives that are also standardizing that might be slower. And then in that case, that's also something you need to consider. Another challenge is the foundations, like discrete log and factoring. That's something that we worked on since the 70s. Lattices, we started on in the 90s, but really the last 10 years. So it's kind of new assumptions. The models with quantum computers, when you want to prove security, is a bit different. And the analysis for security is also different. So it's kind of things that we face, and how do we fit these schemes into applications and protocols and so forth. So there's a lot of migration work and kind of analysis of where it fits in and what kind of security you have that still need to be done. And you have a lot of variations. I think we've been quite lucky so far, like the Diffie-Hellman, discrete log, elliptic curve things, they just work. And there's, like, it might seem complex, but if you compare to post-quantum crypto, it's simple. They just fit in. It's very small, it's very fast. You can do whatever you want with it, and usually you have security anyway. But it's very sensitive when you're looking at the post-quantum schemes, and they might fail in different ways than what we're used to. So there's a lot of different use cases. You need to think about different, how you use them, how you combine them. There might be different standards in different countries. So like European countries and the US might standardize different schemes. It seems like all of them are doing Kyber and Dilithium, or ML-Chem and ML-DSA. But additional schemes differ a lot. And they also recommend different key sizes and parameters and so forth based on applications. So I'm a bit worried and also curious to see how we align, for example, in NATO countries and so forth when we communicate across continents and different standards. Some of the opportunities, like post-quantum crypto is coming whether you want it or not, and whether you believe in quantum computers or not. So this is an opportunity to also be in the front of this field and start today to kind of brand yourself and market yourself and kind of take opinion in this space, and which might give you a lot of extra customers because you kind of you know what's coming and you already tested it and you're ready, and a lot of people have requirements, law requirements that is coming, and they need to satisfy these, and being in the front can give you an advantage. It's also an opportunity to clean up. So we have a lot of old cryptography that we want to get rid of, and now you have to, so why not do it properly? Finally, we do have a lot of experience with implementation, so side channel attacks and how to protect against those is something that we didn't know when we standardized cryptography that we use today, but now we do and can make it right from day one. Linear algebra is in general easier and faster and something people know more about than elliptic curves. So actually when you get used to it, I think people will have a better understanding of the future cryptography than elliptic curve cryptography that we use today. And also this allows for some special applications in the future for privacy preserving computation. This is a whole new topic, so that will be its own talk, but at least now you can do computation on encrypted data, so you don't leak secrets even though you share data across applications and want to be able to analyze private data without someone else looking at it. So that's an opportunity that is coming that is really interesting. That said, if you want to read more, I put the slides on my website. There's a really nice blog post about this topic. Yesterday there was mentioned Bruce Schneier's book on applied cryptography. That was the golden standard 25 years ago. Nowadays I would recommend one of these two books, either Real World Cryptography by David Wang or Serious Cryptography by Jean-Philippe Amazon. These are the books I use in my course. My company have a white paper about post-quantum crypto with also some more information, so that's worth checking out on our website if you're interested. And we're already over time, so thank you, and I'm happy to take questions offline.